Hey guys, thanks for tuning into CMTEQ channel. This is tutorial 3 on power system distribution. What you see here is obviously a cell phone, a charger, and a wall outlet. Now we all know if you plug this charger into your wall outlet, the cell phone will start charging. Now this is assuming that your charger is not broken and also you have a good cable. Then your cell phone will start charging. But what we don't consider is the fact that we've got a power transfer that is happening here. The power is coming from the wall outlet, then some transformation is happening inside the charger, and from there we're transferring that power through the cable into your cell phone so that we can start charging the battery. Now, if you don't have a good cable, if your cable does not have good properties, there will be a lot of power that is going to get lost. Because considering the fact that most cell phones, most smartphones today, they charge at about 2 amps of current, right? So if you have 2 amps of current going through this cable here, and this cable got a high resistance, that means it's not a very good cable. That means 2 amp with a high enough resistance, there's going to be a significant voltage drop. And that voltage drop along the cable will result in your battery not getting the appropriate voltage to charge. Because if this charger here was configured to charge at 5 volt, right? Now you are losing about 1 volt because of a bad cable. So you're going to be getting 4 volt here, and that's not a good condition to charge your battery. So electrical power distributions is all about ensuring that you've got maximum power transfer so that you minimize the waste along your transmission line. So this is the basis of this tutorial and many other tutorials we're going to do about power system distribution. So stay tuned to grasp a good understanding of the principle of power system distribution as we go through this problem. And if you find this tutorial useful, please give it a thumbs up and subscribe to CMTEQ channel. That would be highly appreciated. So what do we have here? We have a 2-wire distributor at 250 volt and loads of 60 amp, 100 amp and 120 amp are taken at distances of 100, 200 and 250 meters respectively from the feeding end. Right? So the feeding end is where the power is coming from. Now, if the resistance of the distributor is 0.1 ohm per 1000 meters of a single conductor, calculate the potential difference across each load point and also the power dissipated in the distributor, and finally the energy lost in the distributor in 8 hours, right? So the distributor is basically that transmission system that is taking power from the feeding end and send it to each one of these loads. And while doing so, there is power losses, right? And we are asked to now calculate that power loss and also the potential difference across all of these loads. Now, before you can start, the first thing here is you have to draw the circuit so that you can actually visualize the problem that you have in front of us. So we're going to draw the circuit here. So let's go ahead and start drawing our circuit. So this is my 2 wires, because we understand that a system is always 2 wire because there is a live and a neutral, or a plus and a minus, right? And here we've got a 250 volt. So this is a feed. And they say that loads of 60 amp, 100 amps and 120 amps are taken at distances 100, 200, 250 meters respectively. So which means at a distance of 100 meters, we've got a 60 amp load. So what I'm going to say now is, I'm going to say, okay, from this point to this point here, I'm going to say this is 100 meters, right? So this is 100 meters. And I'm going to place a load here. And this load is going to be 60 amp. And we've got another load of 100 amp at 200 meters. So which means another 100 meters, right? And we're going to have another load here. And this load here is 100 amp. Then at 250 meters, so which means just an extra 50 meters. Because remember, this distance is from the feeding point. That basically means from this point here. So which means at 250 meters, I've got another load. I'm just going to draw that load again. And I'm going to close my circuit. Alright. Okay, so this load here is at 250 meters and is drawing about 120 amps of current. Alright. So what we have here is, this is also 100 meters. And this is basically just 50 meters. But the whole distance here is supposed to be 250 meters. So what is the first question? The first question is we need to calculate the potential difference across each load point. What is the potential difference? So that is basically the voltage at this point, and also the voltage at this point. So that will be the voltage across each one of these loads. So let's go. Now, the reason why we need to calculate this voltage here is obviously because there's going to be some voltage drop here. So now we first need to determine the voltage drop before we can calculate the potential difference across here. Because the voltage here will be the source voltage minus the voltage drop here. So which means this voltage. So we can call this voltage V60 amp load is equal to Vs, so that V source minus Vd. So Vd will be the voltage drop across here, so across the 100 meter cable. So we know what's the value of Vs. There's no problem there. The only problem, we don't know what is Vd. So now we need to find Vd, the voltage drop across here. So now we go back into our problem statement here. They say if the resistance of the distributor is 0.1 ohm per 1000 meters of a single conductor. But remember, a conductor is always double because it's going this way and it's returning. So which means it is double. So if there is a 100 meter there, there's going to be another 100 meter there. So together it's going to be 200 meters. Right. So what we're going to do here is we first need to do a conversion for this piece of a cable here so that we can know what is the total resistance there. But we have the information. They say at 0.1 ohm we've got 1000 meters. So which means if we can multiply it with 100 meters, we can then find the resistance of 100 meters. Computing this gives us 0.01 ohm. We know that this resistance is only for a single conductor. Now, in order for us to get a complete resistance value for a conductor with a return path, we have to multiply this by 2. So the answer will then be equal to 0.01 times 2, and that's going to be 0.02 ohm. Now that we know the resistance of this section of the transmission, we can then go ahead and calculate the voltage drop across this section here. So that voltage drop, Vd, is going to be equal to I total times the resistance of that 100 meter section. Now, the total current here is simple. We know that there is a 60 amps of current flowing here, and there is 100 amps of current flowing here, and another current flowing here of 120 amps. So which means at this point here, you should get these two currents standing here. So that's going to be 220 amps at this point. So which means at this point, the current must be 220 amps plus the 60 amp. So that's going to be 280 amps. So that's a total current at this point. This section is having most of the current. So we're then going to say 280 times the resistance, which is 0.02, then we can find the answer to be equal to 5.6 volt. So our voltage drop at this point is 5.6 volt. Now we can go ahead and calculate the voltage at this point. So that will basically mean just applying this formula here. We're going to say V60 amps is equal to 250, the voltage from the feeding, and minus 5.6. And this is going to be equal to 244.4 volt. So we know now that at this point here, we got 244 volt. Now you understand how I was explaining the scenario of a cell phone. Now there is a drop. Now suddenly this load here is no longer seeing the whole 250 volt. Some voltage are being dropped, which is a 5.6. So which means automatically this load here will definitely also see some decrease from the 244.4. So that is now what we need to calculate. So we're moving on here. Now we are on this section here. Now we know that the current here is 220 amps at the section. And also this section, there is another 100 meter here. So we're not going to calculate the 200 meters. That is from this point to this point is 200 meter. But we're only going to consider the 100 meter. That is an extra from this point to that point. Okay, so which means the voltage at this point here is going to be V 100 amp is going to be the 244, or rather V60 minus the VD at that point, right? But in order to find VD, we also need to calculate the resistance of this section. But we can see that this section is also an extra 100 meters. So which means the resistance on this section is going to be the same with the resistance of the previous section that we found here to be equal to 0.02. So we're going to say our R 200 meters is also going to be 0.02 ohm. So this gives us an ability now to find this VD. So VD is going to be equal to the current times the resistance, and the current on this section is 220, right, times 0.02, and that gives us a value of 220 times 0.02. We can see that it is equal to 4.4 volt. So this is a voltage drop on this section. Now we can go ahead and calculate our V for the 100 amp load. So the V for the 100 amp load here is going to be equal to the voltage here, which is a V60 that we found to be 244.4. So it's 244.4 minus VD, which is 4.4. And this gives us a value of 240, as we can see there, 240 volt. So now we also have the voltage at this point here, 240 volt, which drop further from the voltage at this point. So far, we already lost about 10 volt. From 240 volt to here, we are at 240, 10 volt gone. Now, let's focus on finding the voltage at this point here. Now, this point is 250 meters from the feeding point, but it's actually only 50 meters from this point here. So which means we need to focus with the resistance for the 50 meter cable. So that is going to be, we have to do another conversion here. Now, as you can see, this 0.02 ohm is for 100 meters. So which means for 50 meters, we just have to divide this by 2. So which means I'm going to deduce that R for 250 meters load point is going to be 0.02 divided by 2, which is going to be 0.01 ohm. Now the only thing left to do here is to also calculate the voltage drop, and we know the current at this point is obviously the 120 amps that's flowing from here to here. So we can say that our VD here will be 120 times 0,01. That's going to be 1.2 volt. So we've got a further 1.2 volt drop here. Now we need to subtract this 1.2 volt from the voltage at this point, which is a V100. So which means the voltage at this point, which we call V120 amp, is going to be equal to 240, right? Because that's a voltage at that point, minus 1.2. And this is going to be equal to, obviously, 238.8. So it's 238.8 volt. So now we've answered question 1. We now know all the potential differences. So from 250 volt, we only get 238 at this point because there are losses along the distribution line. Now, let's find question 2. Now, question 2 here, we need to find the power dissipated in the distributor. Now, this is not the power dissipated across the load. It's not that. Because the power across the load here is going to be big. Because for instance here, you know at this point here, you got 240 volt and you've got 100 amp here. So you can just see how much power is being used here. So that's not the power we're being asked here. We're being asked the power that is wasted across the distribution line. So that power, in order to calculate that, we then need to use this voltage drop and multiply with the current so we can get the power for each section and then combine it. So you guessed it. So which means we can say P total is equal to P for these 100 meters plus P for the 200 meters. We know what we did there. Plus the P for the 250 meters load, right? So that is a power across all of these sections. Now we know that the power on each one of these sections is proportional to the voltage drop on each one of the sections. So this will be equal to P 100 meters. So we know what's the voltage drop there. It is equal to 5.6. So we're going to say 5.6 times the current there, it's 280, like that, plus the power on this section, which will be equal to the voltage drop on that section, 4.4 volt, times the current on that section, 220 amps. So we're going to say 4.4 times 220, plus the power on the last section, so that is going to be the 1.2 volt, times the 120 amps. So 1.2 times 120 amps. Now we can go ahead and calculate this. And we get a total power of 2680 watt, which we can convert to kilowatt by dividing it by 1000. So it's going to be 2.68 kilowatt. So this is the amount of power being wasted in this entire distribution line. All right, now we can move to question number 3. Now question 3, we now need to calculate the energy lost in the distributor in 8 hours, right? So what is the formula for the energy? Now the formula for the energy, we know that E is equal to the power, right, times the time, right? Because energy is calculated over a time period. So from here, we can then replace the value of the power, which is 2.68 kilowatt, times the time, which is given in hours. We can just then add it here, 8 hours. Now from here, just a simple calculation of 2.68 times 8, and I'm getting 21.44 kilowatt hour. Right now, this is a lot of power, energy being wasted. Now imagine if you are buying power from a power supplier company and they are selling you like a 1 kilowatt hour for, let's say, 3 rand, South African rand. So which means automatically you have 21.44 that you have to multiply times 3 rand, and you are losing about 64 rand here, right? You're losing about 64 rand just because your cables, they are wasting energy as you are transferring power from those points to all these loads here. So this is why it is very important to efficiently design your distribution system to minimize the waste and the cost as well. Thank you guys for watching. I hope you've learned something in this tutorial. Please don't forget to subscribe to CMTEQ channel and give this tutorial a thumbs up if you found anything useful. Until next time, cheers. Stay tuned for more tutorial like this.